Hi, thanks for joining us in this video. We're going to finish talking about 12.5. 12.5 was talking about linear equations, both equations of lines and equations of planes. In the last video, we talked a lot about different kinds of equations of a plane and two little examples. We're just going to continue in this video with the more complicated examples. For instance, let's find the equation of a plane with the point P 3, negative 4, 5, and containing the line L1 x minus 2 over 2 equals y plus 1 over negative 3 equals z plus 3 over 5. Do you remember what this kind of a equation of a line was called? This is a symmetric equation. If you feel like how you could do the two things we need to do, which remember is get a point, we need a point, which we again check, easy, and a normal vector. Can you think of a way to get both of these things? Sometimes a picture will help. So again, I'll just cheat and draw my plane. I have my line, L1. It goes forever in this plane. And I have a point in the plane that's not on that line. Hint. I guess I should have said that in the directions. It's very important that that point is not on that line. Think about why. Think about why. That's enough of a drawing that you should feel, if you have a good geometric sense, a good spatial reasoning sense, of exactly what you want to do here. So what you want to do is find the direction vector, because that's going to be one vector in this plane. Can you right now, looking at the symmetric equation, tell me what the direction vector would be? Should be easy. It's literally the denominators. Step 2. If we try to do what we did in the very last example, it would be good to have a different vector. It'd be good to have a different vector in that plane, and then we could do a cross product. So this is a little bit tricky. The idea is to find any other point on that line and then get me a new vector like that. And just so you can finish visualizing it, that would make the normal vector up here. And then we'd be done when we got out of the plane with the normal vector. So 2, find a point on the line, on L1. Do you have a good idea of how to find a point on a line at this point? No pun intended. Okay, you should easily see a point that the line was based around. Cough, cough, cough. What if I told you a point was 2, -1, -3? Do you see where I got those numbers from? I'm not just making stuff up. These numbers up here in the numerators are exactly coming from some sort of standard form where we used a point and a direction vector. This should sound familiar. If it's a little tricky, go back and watch the earlier videos for this section. So 3, get vector from P to other point. What do I mean by that? Between 3, -4, 5, and 2, -1, -3. Doesn't matter which direction we go. Not particularly. Not particularly. I'm just going to do in the natural order it's here. -1, 3, -8, 4. Do D1 cross V. This will get us the normal vector, right? Cross products should be seen as a way to get normal vectors. You should all try this out. Try to get me this normal vector here. Try to tell me what it would be. Try to fill out the I, J, and K columns and then compute. So if I'm doing D1 cross V, it should be like this. The other order shouldn't matter. It would just change the sign. Through the magic of editing, I'm about to shrink this. Poof. I have 24 minus 15 in the I direction. Negative 16 plus 5 in the J direction. 6 minus 3 in the K direction. Or 9I plus 11J plus 3K. No easy way to scale that up or down. Do we have a point? Do we have a normal vector? Yes and yes. So we're going to stick it all together. You should right now be able to do that. You should right now be able to write this equation in the vector form or the scalar form, more useful, or the general form. Go ahead, try it out. 3, 2, 1, here I go. 9 x minus my x coordinate plus the j component, y minus or y plus the the y coordinate, 3 times z minus the z coordinate. And that's beautiful. A good enough equation for me. Couple more examples here. What about a plane? Sorry. Equation of a plane with P as 2, 1, 1, Q as -1, 3, 2, and perpendicular to 2x plus 3y minus 4z equals 3. Pause. Right now, can you tell me what surface that is? There's a big hint. It's not a line, that is a plane. What does it look like when two planes are perpendicular to one another? When two planes are perpendicular, it'll look like this. And it's going to meet up with like somebody like that. And you see how they generate a line in their intersection? Cough, cough, cough. That might be something else we talk about. But right now, I have like P. Oh, wait. Sorry. I have a point P. I have a point Q. And I'm perpendicular to this other plane. We still need a point and a normal vector. We can't use this normal vector here. We can't use n equals 2, 3, -4. Why? Because that normal vector is perpendicular to the red plane. And now maybe you see what's going to happen here. Well, if I have that red vector that's perpendicular to the red plane, and I have this vector between these 2 points, can't we do those cross products? So n must be in the plane we need. This is because it's in our plane, the plane we need. We want. So do actual n equals like PQ cross 2, 3, -4. And that's what we would do to get the normal vector. This video is getting a little long. I already did a few examples of how you would do that cross product. Feel free to ask me to clarify this further in office hours, but we still have a point. After you do that cross product, you'll get a normal vector, and we'll be on our way. I want to move on to other more interesting, more unique examples. I'm just trying to show you the kinds of stuff that can happen. So, let's continue with a really important note. Two planes are parallel. We talked about this in one of the videos. If the normal vectors are parallel. So we also will have the idea that two planes will be perpendicular. I'll write are perpendicular if the normal vectors are perpendicular. Okay? And what about everything else? Can two planes be skew? Can two planes be non-parallel and non-intersecting? No. Planes are really like the more close equivalent to what a line is doing in 2D. A plane using those 2 dimensions is more like how a line uses 1 out of 2 dimensions in a plane. A plane is using 2 out of 3 dimensions in a space. So, if planes intersect, remember they can't be skew, the angle between planes is the angle between normal vectors. Yuck. Vectors. Okay? So what am I saying? Let's do an example of this. Let's try to make this a little more concrete. Example. Given 3x minus y plus 2z equals 2 and 2x plus 3y plus z equals 4, find the angle between the planes. Now again, they don't have to tell you those are planes explicitly. You should know. How do I know? There's no multiplying between the variables. All the variables have 1 power. It suggests that these planes are going to not be parallel. How could you check if they're parallel? It's always a good idea. Check. Is this a trick question? Parallel. And 1 would be what? Can you find the normal vectors of these 2 planes? Can you do that right now? The normal vector of the first plane is 3, -1, 2. And for the second plane, it's 2, 3, 1. Are those 2 scalar multiples? No. So they're not parallel. These are not scalar multiples. I don't know what I was thinking. Not parallel. Okay. Are they perpendicular? How could you check that? How do you check perpendicular? How do you check orthogonality in this class? We would check it by doing n1 dot product with n2. To check parallel, you could check the cross product. It's going to take a while though, right? And what do you get if they're perpendicular? What would this output be if it was perpendicular? So I'm going to do this cross product, this dot product, this dot product, this dot product. 6 minus 3 plus 2. I'm getting 5. not perpendicular. Why? Because it's not 0. Not perpendicular. So then we could find the angle. And how would we find the angle? Wrapping this all up, you would do cosine theta equals n1 dot n2 over the size of n1 times the size of n2 and solve for theta. I hope that's not a hard thing for you to do at this point. Again, if you want to see all the details, please feel free to ask me in office hours. For now, I'm going to, again, try to turn our attention to something more interesting. If you're confused about how that process works, please go check out the video on dot products, and you'll see this is a pretty straightforward application. And then we would find the angle theta. If you wanted to check your work, theta would be about 64.623 degrees or 1.128 radians. If you get a different number, I don't know, let me know. Maybe we made a mistake, or maybe I made a mistake. Example. Find the intersection of 2x minus 3y minus z equals 9 and x equals 2 plus 3t, y equals negative 1 plus t, z equals 3 minus 2t. Can you right now tell me which is which? Right? This may be a long time since you've seen this other guy. The guy on the left, this is a plane. And the guy on the right, this is a line. It should be clear to you they look very different. And again, the only confusing part is that the plane is a linear equation. I think it wouldn't be that hard to say some of you were able to come up with the right method to solve this kind of a thing, to solve this intersection. I'll give you a chance to think about it. Pause the video if you want to actually really ponder it. 3, 2, 1. We're just going to substitute line parameters into the plane. What does that mean? Well, I have 2 times the x stuff minus 3 times the y stuff minus the z stuff equals 9. So what we got? Like 4 plus 6t plus 3 minus 3t minus 3 plus 2t equals 9. 5t equals 5. T equals 1. Is that the intersection? No. We can plug that value of t, get x equals 5, y equals 0, z equals 1. There's only one point of intersection. What would happen if the line was in our plane? Well, there would be infinitely many intersections. You would get something that it's always true. All values of t would work. T would drop out of the equation. You would get a true statement. Something like 9 equals 9 is what I'm saying. And then that would show you that the line was in the plane. Okay, like if you got 9 equals 9 after doing all the simplification, it's like, oh, all t, which means the line is in the plane because there's no value of t that would get you out. In case you're having trouble picturing it, again, same old drawing here. We have a plane, and then my line is like a laser beam from space. It hits and then goes through. Okay? And that we're just finding the one point where that line hit that plane. Make sure you do the sound effects, like Bob Ross says. The sound effects make it easier to draw, always. Okay, one last example. Uno más. Find the intersection of 2x minus 3y plus 4z equals 3 and x plus 4y minus 2z equals 7. Right now, can you tell me what those two are? Those two are planes. We're assuming they're going to intersect. Remember, planes could be parallel, but let's just assume they intersect. How do two planes intersect? We already did one where they were perpendicular. So those two planes are floating in space, and again, try to picture that one's underneath the other. Their intersection's kind of complicated. I hope we're okay with the image. How are these two planes going to intersect? Well, this region that I'm drawing lives on both planes. It's both in the blue plane and the black plane. And what did I draw? So two planes. Oh no. Two planes will intersect. Again, they could be parallel, but if they do intersect, to form a line. So we need, what do we need? We need a point. Oh man. We need a point and a direction vector. Now here's the issue. Here's the issue. For my blue guy, the normal vector is going like that. It's not at all with the line, right? Not in the direction of the line. And my black vector, maybe the normal vector is like this, right? Also not with the line. But the way I drew it, it should be clear what we want to do. While I let you think about this, I'm going to say the first step is find my two normal vectors, please. If you can't do this right now, you really got to rewatch these videos. Maybe slow it down. I don't know. It should be really clear after doing all these examples. I got 2, -3, 4. And I got 1, 4, -2. That should make sense. Now, how can we translate this into a direction vector for my line? Do you see how they are acting in a, orthogonal direction to that line? Both blue and black, if taken together, are going to be orthogonal to that line. And orthogonal is a big trigger word for you all. It should mean, okay, we're going to use the direction vector as their cross product here. I am actually going to find this here. Why don't you go ahead and try to do it? Try to give me this direction vector. Practice makes perfect. All the old stuff that everybody's parents like to say. Maybe grandparents now. I don't know, man. Last chance to pause the video and try to find it yourself. We got 6 minus 16 in the I direction minus -4 minus 4 in the J direction plus 8 plus 3 in the K direction. -10 I hat plus 8 J hat plus 11 k hat. That's our direction vector. Now, how do I get a point? Here's a real hack technique, and they would work in almost every single other problem. But first, I'm going to shrink some stuff down. In a lot of problems, if we need to find a point, online, set x or y or z equals 0 in the system. To be really clear what I'm talking about here, 2x minus 3y plus 4z equals 3. X plus 4y minus 2z equals 7. We're just gonna, hope that the line eventually will have x equals 0 on it, basically, or y equals 0 on it, or z equals 0 on it. Again, you know this is very, very likely. Lines go on forever. They're very likely to hit the planes. If something's going wrong, the equations were probably simpler to start with. I'm going to do y equals 0, okay? Y equals 0. I don't like -3 and -4, so I'm going to do y equals 0. And what comes out? We get 2x plus 4z equals 3. And x minus 2z equals 7. Can you solve this equation? For 2 variables, 2 equations, we should be able to. If I multiply by 2 and add, I'm going to get 4x equals 17. Sorry, that's an uglier number than I thought. X would be 17/4. If I plug that back in, I get z equals -11/8. And again, y equals 0. Magic of editing, 0, -11/8. Direction vector equals -10, 8, 11. I don't know why I'm changing it to component form, but there you go. X equals 17/4 minus 10t. Y equals 8t. Z equals -11/8 plus 11t. Ta-da. Not very nice numbers. It's not that bad. I know you can do it. Go out there and destroy the homework. All right, I'll talk to you in the next video. We'll finish chapter 12 and talk about some interesting looking surfaces. Planes are nice flat surfaces. What if we got all wiggly woggly, curvy? Thanks for watching. Have a good night. Bye.